Hi guys, so today we're going to be talking about in-memory database. So first off, I'm going to go over the table of contents, and I'm going to first introduce exactly what is in-memory database and define and explain what it is. And next I will explain how in-memory databases work and how durability is used. Then I will explain what in-memory databases is, how it's used, and provide some examples, and then explain the advantages versus disadvantages. Then go further on talking about temporary databases and the storage. And last but not least, I will provide a conclusion and overview about what we learned in this video. So first off, let me give a little introduction about in-memory database systems. They are a growing subset of database management systems, or DBMS software. They are emerged in response to new application goals, system requirements, and operating environments. And I'm going to go further on into explaining exactly what it is, and we're going to put a definition to this term. So what exactly is in-memory database? The definition terms it as an in-memory database system is a database management system that stores data entirely in main memory. This contrasts to traditional or on-disk database systems, which are designed for data storage on persistent media. Because working with data in memory is much faster than writing to and reading from a file system, IMDS can perform applications data management functions an order of magnitude faster. Because their design is typically simpler than that of an on-disk database, IMDS can also impose significantly lower memory and CPU requirements. To make the long story short, an in-memory database is a database that keeps the whole data set in RAM. What does that mean? It means that each time you query a database or update data in a database, you only access the main memory. So there's no disk involved in these operations. And this is good because the main memory is way faster than any disk. So how exactly does it work? Since it's a database whose data is stored in a main memory to facilitate faster response times, source data is loaded into system memory in a compressed, non-relational format. In-memory databases streamline the work involved in processing queries. In its simplest form, main memory databases store data on volatile memory devices. These devices lose all stored information when the device loses power or is reset. So in this case, IMDBs can be said to lack support for the durability portion of the ACID, or atomicity, consistency, isolation, durability properties. Volatile memory-based IMDBs can and often do support the other three ACID properties of atomicity, consistency, and isolation. Traditionally, databases can be characterized by the four attributes commonly referred to by the acronym ACID: atomicity, consistency, isolation, and durability. As soon as you stop persisting a database, you lose durability. So this is what is lost with an in-memory database. Aside from methods of copying database contents to another durable location, an in-memory database can be subject to data loss if something stops working. The remaining attributes, atomicity, consistency, and isolation, are what differentiate an in-memory database from simple data held in some shared memory. Atomicity is the word used to describe transactional behavior where all changes are committed to the database as an all-or-nothing operation. Isolation is the word used to describe what transactional changes other processes see. They can never be allowed to see partial transactions. In its most basic form, shared memory does not enforce atomicity or isolation. That is fine as long as there is only one process using the data, but that defeats the purpose for shared memory. How is durability used? There are snapshot files or checkpoint images which record the state of the database at a given moment in time. The system typically generates these periodically, or at least when the IMDb does a controlled shutdown. While they give a measure of persistence to the data and that the database does not lose everything in the case of a system crash, they only offer partial durability, as a recent changes will be lost. For full durability, they need supplementing with one of the following: transaction logging, which records changes to the database in a journal file and facilitates automatic recovery of an in-memory database. Non-volatile DIMM, a memory module that has a DRAM interface, often combined with NAND flash for the non-volatile data security. The first NVDIMM solutions were designed with supercapacitors instead of batteries for the backup power source. With this storage, IMDb can resume securely from its state upon reboot. In-memory databases are allowed to use shared cache if they are open using a URI file name. If the unadorned memory name is used to specify the in-memory database, then that database always has a private cache and is this only visible to the database connection that originally opened it. However, the same in-memory database can be opened by two or more database connections as followed, which is shown in the 2 bullet points, those 2 links. This allows separate database connections to share the same in-memory database. Of course, all database connections sharing the in-memory database need to be in the same process. The database is automatically deleted and memory is reclaimed when the last connection to the database closes. If 2 or more distinct but shareable in-memory databases are needed in a single process, then the mode equals memory query parameter and can be used with the URI file name to create a name in memory database, as shown below in that link. When an in-memory database is named in this way, it will only share its cache with another connection that uses exactly the same name. So how is in-memory databases exactly used? In-memory databases are most commonly used in applications that demand very fast data access, storage and manipulation, and in systems that don't typically have a disk, but nevertheless must manage appreciable quantities of data. An important use for in-memory databases systems is in real-time embedded systems. IMDS running on real-time operating systems, RTOS, provide the responsiveness needed in an applications including IP network routing, telecom switching, and industrial control. IMDS manage music databases in MP3 players and handle programming data in set-top boxes. In-memory databases, typically small memory and CPU footprint, make them ideal because most embedded systems are highly resource constrained. Non-embedded applications requiring exceptional performance are an important growth area for in-memory database systems. For example, algorithmic trading and other applications for financial markets use IMDS to provide instant manipulation of data in order to identify and leverage market opportunities. Some multi-user web applications, such as e-commerce and social networking sites, use in-memory databases to cache portions of their back-end on disk database systems. These enterprise-scale applications sometimes require very large in-memory data stores, and this need is met by 64-bit IMDS editions. In addition, applications where response time is critical, such as those running telecommunications network equipment and mobile advertising networks often use main memory databases. IMDb's have gained a lot of traction, especially in the data analytics space starting in the 2000s, mainly due to multi-core processors that can address large memory and due to less expensive RAM. So what are some examples of in-memory databases? Here below I've listed SQLite, Apache Derby, HyperSQL, and H2 database. So what are some advantages and disadvantages of in-memory databases? The main reason to keep a database in memory is performance. Reading and writing data that is purely in memory is faster than data stored on disk or on a flash drive. The corresponding disadvantage is that all data must fit in memory. This is increasingly affordable, but memory sizes are still multi-gigabyte while disk size can be multi-terabyte. It is necessary to buy adequate memory or limit the size of the database. This could also mean potential loss of data and limit on the database size. Some of the advantages would be a persistence in memory database is loaded from disk image when it is open, and changes are automatically saved back when it is closed. A volatile in memory database is empty when it is open, and all data is discarded when it is closed. The third type is a read on open, which automatically loads data from a disk image when open, but changes are only written on demand. So to summarize, the advantages of using RDM as an in-memory database is that it provides transactional multi-user safety, where a shared memory solution requires a lot of work to do this. It also provides greater performance than durable solutions. So what exactly are temporary databases? When the file name of the database file handed to SQLite 3_open parenthesis or to attach is an empty string, then a new temporary file is created to hold the database, as shown below. A different temporary file is created each time, so that just like as with the special :memory: string, two database connections to temporary databases each have their own private database. Temporary databases are automatically deleted when the connection that created them closes. Even though a disk file is allocated for each temporary database, in practice, the temporary database usually resides in the in-memory page or cache, and hence is very little difference between a pure in-memory database created by :memory: and a temporary database created by an empty file name. The sole difference is that a memory database must remain in memory at all times, when parts of a temporary database might be flushed to disk if database became large or if SQLite comes under memory pressure. So right now I'm going to talk about the different storage types. So there's two main storage types in memory database storage requirements: permanent media to store committed transactions, thereby maintaining the durability for recovery purposes if a database does need to be reloaded into memory, and permanent storage to hold a copy or backup of the database in its entirety. When processing comments, disk IO performance is the biggest bottleneck to performance, and minimizing IO overhead is critical. This suggests the best possible storage media to use is flash. Moving flash closer to the processor reduces latency, and so PCIe SSD or the recently released range of NVDIMM memory channel storage devices provides the lowest latency possible. Memory channel storage puts flash on hardware that uses the DIMM form factor and plugs directly into the motherboard of the server, providing solid-state storage on the DRAM bus. This results in extremely low latency IO, but does not require BIOS changes and operating systems drivers to allow the OS to identify the memory as non-volatile. BIOS amendments are required to prevent the server failing the memory on post-boot time checks. So last but not least, let's go over the conclusion and an overview of what we just learned. IMDb, also known as the Main Memory Database System, or MMDB, or Memory Resident Database, is a database management system that primarily relies on main memory for computer data storage. It is contrasted with database management systems that employ a disk storage mechanism. Main memory databases are faster than disk-optimized databases since the internal optimization algorithms are simpler and execute fewer CPU instructions. Accessing data in memory eliminates seek time when querying the data, which provides faster and more predictable performance than a disk. Instead, in-memory database solutions have logic specifically adapted to work with data in DRAM. However, system memory is volatile, which means in-memory databases only conform to 3 out of the 4 ACID model of database characteristics: atomic, consistent, isolated, and durable. Of these, durability cannot directly be served by in-memory databases solutions because data is lost when power is removed from the server. These include keeping additional copies of data in clustered and scale-out databases that allow systems to keep running by replicating updates to one or more standby systems.